Okay, I'm back. I hope it doesn't break again. I'm not sure why it does that. Okay, so Valeria had a question that she thought she couldn't properly express, but I mean, you can call me, Valeria, and I can talk to you. You can just call me now if you want. If you think that will be better. The point is, I mean, I think I've answered your question. The arrow goes to the right of the value. The only way that the area to the right of the value is so small is if we're over here. And then that gives us this value. So to find out where we are, to find out the value of z, we need to either, if you look up this number in the table, you're going to get this one. You're not going to get this one. That's what's going to happen. So if you look up this number in the negative table, you're going to get negative 2.8. That's not the right answer. It's positive 2.8. The reason is because the tables only give you the area to the left. Yeah, you're not interrupting the class. It's part of the class to explain these things, but yeah, you can call me after. All right, so if we looked up this number in the negative table, we would get the answer negative 2.8. That's not the right answer it's not the complete answer, but it might be a stepping stone to the answer if you realize that you got the left side and the answer is really the right side, 2.8. And the answer is also 2.79 or negative 2.79. And then you average those to get the final answer. And the same thing with 7. If you look up this number, you get the negative result because it's of the symmetry of the table. You will get the result on the left side. So if you looked up 0.0100, that would correspond to negative 2.33. So if we did that and we go to, I went too far. So if you looked at 0.0100, the better answer is this one. This is closest to 0.0100, so we pick that, negative 2.33. But sorry, where was I? So that will give you this answer, but that's not the right answer. The area that I want or the one that I'm giving, is to the right. So it's the positive version that I want. In 7, this is just a general this is just a general note about the whole section. Note 1, use the positive table. I guess it should say if the probability is greater than 0.5, and then re-average between two middle values. Like, this doesn't even apply to this question. This is just a general comment. Maybe I can change the word since or to if. But that's a weird comment that I'm making even, because if probability to the left, I should probably edit that. So if the probability to the left is greater than 0.5, you need to use the positive table. Then I say we average between two middle values if no single center value. And I probably should put brackets. This is just very poorly written. And like this, it's like this note got moved from somewhere. So that's just a general comment. It has nothing to do with this one here. Thank you for reading the notes. All right. I hope that helps, but you can call me later if you still don't get it. It's not clear. All right. All right, let's do the last part. So did you have any questions about the test? I promised if you have questions about the test, I was going to answer them first. Uh-oh. Okay, no questions about the test? Yeah, tomorrow we should be halfway through the course, so we have to be on regression. We have to get through regression today. All right. So now I'm going to link what we learned about Z type 1 and type 2 problems to any general normal distribution. And the way that I'm going to do that, and I think I do a good job in the videos explaining this, but if you didn't get around to the explanation, I'll do it here. Notice in the example that we began with, the example regarding heights of women, we could refer to each of the broader tick marks, this 68, for instance, for that variable x, for the value 68. 68 is also 2 standard deviations above the mean of 64. This is important to me because with that information, then I can use the standard normal table to find out what's the chance of seeing a woman 68 inches or shorter. 70 is 3 standard deviations above the mean of 64. Again, I can use that 3 with the standard normal table to determine what's the chance of seeing a woman less than 3 standard deviations or 70 inches. And 58 is 3 standard deviations below the mean, and I can use that as -3 whereas this one was +3 and this one was 2. And I can use the standard normal table to understand what's the chance of seeing women shorter than 58 inches. Okay, so I can transform all the values, not just these ones, into standard normal values of up to 2 digits to be put on the table. So how do we do this? This is actually the formula to get us from 68 to 2 and 70 to 3 and 58 to -3 and 82 to what and 40 to what. So these are numbers that are off the chart, but I could still transform them. So this is the formula to transform between x and z, and it gets me to minus the mean and divide by the standard deviation. In other words, when I divide by the standard deviation, I'm standardizing. I'm turning these values into z's, which are units of standard deviations from the mean. Then once I do that, once I transform every value of x into z, I could solve questions about those using the standard normal table. I can do backward problems, type Z type 2 problems, or I can do type 1 problems as well using Z, finding probabilities. So let's just confirm that. So if I take, remembering that mu, that x is distributed normal with a mean of 64 and a standard deviation of 2. Then the z must be equal to 68 minus 64 divided by 2. which is 4 over 2, or 2. So that's how you get the 2. 70 minus 64 divided by 2, which is 6 over 2, which is 3. 58 minus 64 divided by 2, which is negative 6 over 2, which is negative 3. So those ones we knew. What about 82? 82 divided by minus 64 divided by 2, what does that give? That's 9 over 2. Is that 9 over 2? 82 minus 64 is, oh yeah, it gives you 9. Let me do that again. It's 18 over 2 is equal to 9. Okay, so that's 9 standard deviations above the mean. And then 40 minus 64 divided by 2, that's going to be a negative. Is 24 divided by 2, or negative 12. So it's very far, it's very much in the outliers, okay? So a woman 60 inches is a deep outlier, very short. And a woman in women 58 inches is technically on the borderline of outliers at -3 standard deviations from the mean. So do you have any questions about this? Converting or transforming from these into standard deviations from the mean. So this is important so that we don't have to, sorry, so that we aren't restricted to just looking at the broader tick marks, 68, 70, and 58. Which are 2, 3, and -3 standard deviations from the mean. I can find other ones. I can look at 65 now, or 74. Numbers that were not on the, that we didn't have information on using the 68, 95, 99.7% rule. So what is this I'm talking about graphically? Let's say we started with a distribution I'm going to put it here. I think that's how I did it. So let's say we start with this distribution that is normal with a mean of 64 and a standard deviation of 2. So we would have 64 in the middle, 66, 68, and 70, let's say. And then this way, 62 in this direction and 58. So what I want to do is I want to convert that to a distribution that is centered at 0. So I'm going to take x minus mu, and when I do that, it means take every single value of the distribution and subtract off the mean. So then this will be, because I'm going to do that to every single value, sorry, I'm having trouble here. That should be the same as the other one. Maybe I'll just duplicate it, see if I can duplicate. I did it. Okay, so now I've shifted it over. What just happened? Okay, now I've shifted it over so that every value is subtracted by 64. If I take 64 minus 64, this puts me at 0, right? If I take 66 and minus 64, that leaves me 2. If I take 68 and minus 64, that gives me 4. And if I take 70 and minus 64, that gives me 6. And then similarly, I would get these by minusing 64. No, that was right. So this would be a normal, also the same shape. All I've done is shifted it over. And so this becomes a normal distribution centered at 0 with a standard deviation of 2. Now, how do I convert that into a standard normal? I would have to divide every single value, and that means everyone in between 2, but I'm just showing you for the drawing's sake. I divide every single value by 2, so I convert them into standard deviations from the mean. Oh, actually, that's not going to work because I'm going to, if I standardize it, or if I divide it by every value by 2, I convert it to a z. So this will be more narrow now. And if it's normal, the peak has to go up. Okay. So it's a tighter distribution anyway, relatively speaking. And this would be z. So what have I done? So what I've done is translated 64 inches to standard deviations from the mean. So over here, 64 is 64, but it's also the mean. 66 is 66, but it's one standard deviation above the mean. So that 64 marks the mean as 0, and then 66 translates into one standard deviation from the mean. 68 is 2 standard deviations from the mean, so it's translated into 2. And 70 marks 3 standard deviations from the mean. So I've converted this into z so that I can talk about the distribution in relative terms, relative to its mean, and use the standard normal table. So, what can I do with this? Here I ask you, in a set of problems, now solve these problems not using the 95, 99.7 rule. I want you to use the standard normal distribution. You could do this in Excel using the normal distribution, but you should be able to also do it the way I'm showing you right now. So what you do is first you standardize, you convert all these values of x into z, and then use the table to answer the question. So what you do is standardize first. So 60 gets converted into 60 minus 64 over 2. X is converted into a z, and 68 is converted as well. We know the answer to this, but so this question just reduces to 2 standard deviations from the mean, and we know that it's roughly 95%. But to proceed with solving it, oops. Now what I'm going to draw from now on are the z's. I'm always going to draw the z. So you want this area. We know it should be about 68%. But what we have to do is get the values from the table. -2 and 2. And then we take the bigger one minus the smaller one. So we'll get them at the same time. Let's see. -2, so 2 is 97, 72, and -2 is 0.0228. Now you should remember these. We actually worked with these before as well. So 0.0228 and 0.9772. Which is just about 95% if you round it to whole percentages. Any questions? So this is known as a type 1 problem. It's basically looking for a probability. But I begin with a distribution that's not standard normal, and I convert it to standard normal so I can use the standard normal table. What about x greater than 82? This would be converted also into z, and you take 82 minus 64 divided by 2, which is z greater than we did this, right? It's going to be 9. No, it was over there. So this is greater than 9. Now what would that be? Is there anything greater than 9 according to our chart? Where is 9? I'll make that line again. So 9 is over on the right. No, it could be way over here. Is there anything out there? Probably just close to 0. Remember, I always draw Z. Okay, now that I learned how to relay the two distributions, I always draw Z. Now, these are numbers that are not on the major tick marks. They're not on the major 1, 2, or 3 standard deviations from the mean. They're somewhere in between. So let's try that one. Now I want to draw Z, so I need to standardize this. I need to convert each of these values into Z. So this converts into 11 over 2, or 5.5. Negative? Did I do something wrong? Hold on. Four 4.5. So negative 4.5 less than Z and 0.5. So to draw this, it's not an accurate drawing, but anyway, it's too far. It's too, let me do this again. Let me see if I can move this over. There. All right, so 4.5 is over here, and 0.5 is just above 0. Now the area to the left of this one that's off the chart, anything off the chart we said, this is so small, we'll just call it 0. And then to the left of 0.5, we need to check that. To the left of 0.5, we got to go to the positive table and go up here. The answer is 0.6915. Any questions? So the answer I get is 0.6915. Because if I subtracted this, it would just be this amount. Because it's just 0. These things are not attached. I'm gonna lose stuff. Any questions while I'm tinkering with this? Did I get it all? Nope. Anyway, you get the point. I'm not going to bother with the other one. So that's how you solve these problems. So that's that. That's standardizing. What about the backward problem? How do we conduct the backward problem? Well, we have to do things backwards. So I'm going to start. So the first thing I did here, right, was standardize, and then I drew the chart, or drew the curve. So I'm going to do this backwards. I'm going to make the curve, and then go back from Z to X. So everything backwards. So I'm going to draw the curve first. That was weird. That's not what I wanted to do. So I draw the curve first. This is my Z curve. And I want to make it bigger. All right, so then I have that. I want to find the 97.72th percentile. It means find the position X where 97.72% of the observations are to the left. So since 0 was here and that's 50%, this is going to be, this must be over here in Z. Now I'm going to find out how many standard deviations we are away first. And then I'm going to convert it back into this variable x. So since this will help me find where I am relative to the mean, that later I can translate it or transform it back. So first I answer this question, and I'll call this step 1. So I go to the positive table and look for 9772. And I find 0.9772 at 2. So 2 standard deviations above the mean. To the left of that is 97.72% of the observations. So Z is 2. So now the next step is to convert 2 standard deviations from the mean into an x. X equals, watch this, 2 standard deviations from the mean. See what I did? I put in symbols what I was saying in words. 2 standard deviations from the mean. And now that's how I get x. I plug this in. X equals 2. Sigma is 2. And the mean is 64. This gives me 68 inches. And that is my answer. So I refer to this as unstandardizing. So we unstandardize. You take x, sorry, you take, to get big X from Z, you take sigma standard deviations from the mean. Now you'll notice that this is the same relationship as when you standardize, except I'm solving for x rather than z. If you take this expression and solve for x, you'll see that they're the same. You see? All right, let's do the next one. So this was a matter of doing the backward problem for Z and then converting. So this is the new material. You have to unstandardize what you get, turning from Z to X. But this is basically essentially the backward problem, trying to find how many standard deviations you are away and then converting it into the units of the problem. All right. Oh, I explained it all here in the notes. Here's another problem and a solution. So given x is distributed with a mean of 64 and a standard deviation of 2, at what height would a woman be among the tallest 1% of women? So to be among the tallest 1% of women, where would you be on this in terms of Z? Would you be here? Well, here in the middle, you'd be in the top 50%, right? Because you have 50% to the right and 50% to the left. Over here, you're getting, you're among a smaller group of women. Maybe about here is 1%. So this is where I want to look, where this is 1%. So this denotes statistical notation for what I've drawn here. This is the position in terms of standard deviations from the mean, but then I have to convert it to the units of the problem. So I actually want to move this all over here. So this is step 1. So which Z would give me that result? So either you look on the positive table for 0.9900 because that's the area to the left, or you look up this number on the negative table and then use the positive version. So those are your options. So this on the positive table or this one on the negative table. And then you have to change the sign. Of Z. I use a script C for lowercase. So let's do both. We'll begin with the positive table. So looking for that number in the positive table, let's clean up the table. Now looking for 0.9900. So 0.9900, if you remember, you're starting to remember these numbers, the best answer is 2.33, right? That's the closest. That's the one we pick. So Z is equal to 2.33 because of that. If you were to use the negative table, you would get negative 2.33, but you have to remember to change the sign because we're looking on the top tail, not on the bottom tail. So if you look for 0.0, let me clean up again. If you look for 0.01, what was 0.01001%. Looking for 1% in this table brings us to here. That's the closest. And it's negative 2.33, as I promised you. Oops. All right, so that's step one. Step two involves converting for x. X equals to z standard deviations from the mean. So then x is equal to 2.33 standard deviations, there's a 2, from the mean. So the final answer is 68.66 inches. Any questions? So first you recognize this is a backwards problem. I give you a probability and I ask for the value of a variable. So we begin by finding its position in terms of standard deviations from the mean. And we find out that it's 2.33 standard deviations above the mean. And the second step is to convert that to the units of the problem using the mean and standard deviation. So I convert z standard deviations from the mean, in other words, 2.33 standard deviations from the mean. And that's it. Questions? Given x is distributed normal with a mean of 64 and a standard deviation of 2, at what height would a woman be taller than 97.5% of women? So how would we express that in statistical notation? What we're saying is we want to see the percentile. We want to find x, the percentile, in particular the 97.5th percentile. .975. So we draw it. G. That didn't work. Let's draw a new one. So step one, have a position where this person is taller than 97.5% of other people. How many standard deviations above other people will the person be? Oh, I'm going taller than, sorry. No. Yeah. I know you're trying to read tall, but she's taller than, so she's here, taller than all of these people. So that's why I'm going left. She's over here, but because she's taller than these people over here. Is that okay? I know students get tricked with the terminology, but just think about it. She's taller, so she has to be up here. These people are all shorter. Better? So she's taller than 97.5% of people, so she's tall. She's up here and everyone else is down here. So then you look that number up inside the table in the backward problems, right? We look inside and out. So I look for 975. And the closest we have, this is perfect, 975, is 1.96. What, 1.96. So that value is 1.96 standard deviations above the mean. So the next step is to convert that into units of the problem, into inches. To convert, I use the definition of z standard deviations from the mean. I unstandardize 1.96 standard deviations from the mean, and I get my answer. So this is the last instructional problem I'm going to do. Now I'm going to assume, like, we're going to use either any of the things that we've learned regarding standard normal distribution, a normal distribution, or using just the simple 68, 95, 99.7% rule. All those are up for grabs. We're going to use whatever we have to answer the following questions. But I've just completed teaching you all the techniques that you need for this unit. Okay, questions? Very good, Alexandra. Valeria, what number are you looking at? I think you picked the wrong one. Just to remember, at 2 standard deviations, you have approximately 95%, right? And then this is 2.5% and this is 2.5%. This is at 2. I have to be careful about writing that because it looks like a Z. And I don't want it to be a Z. So that's why at approximately 2, we find 97.5. Oh, okay, very good. All right, so that's it. Those are all the tools. You have all the tools now. Now you have to learn how to use them. So we're going to practice a little bit more. It's 7:30. It's okay. Let's go on to these. So now let's apply what we learned here. Here you have 2 basketball players, one a male, one a female, and I want to compare them, but in their own group, among their gender. Michael Jordan's height is 78 inches. Rebecca Lobo's height is 76 inches. So he's taller than her. However, in their gender, who's a relatively taller basketball player? How will I figure that out? Well, I'm going to make them relative. I'm going to convert these numbers into relative measures. I'm going to say, how many standard deviations is Michael Jordan relative to to other men in general population? So I'm going to standardize 78 and convert it into standard deviations from the mean. And when I do that, what do you get? So he's an outlier. He's 3.21 standard deviations above the mean. He's an outlier. But when you check Rebecca Lobo, 76 minus her mean, divided by her standard deviation, she's much more an outlier. She's much taller. So she's the taller of the two, relatively speaking. So I didn't ask you for probabilities. I just wanted you to use a tool to explain who's taller. And you've done that by standardizing. You can compare those values now. You've made them comparable. Ready for the next one? right. All right, so here's another problem. Here's another example. I want to compare two students. One that took the SAT and the other one that took the ACT as college for their college admissions exam. So Eleanor got 680 on a test that has a mean among, millions, hundreds of thousands, if not millions, of individuals having taken it. Mean is 500 and the standard deviation is 100. Gerald took the ACT, a different test. His score was 27, where the mean is 18 and the standard deviation is 6. So both are above the mean, but I want to see who's the better student. So who has the better score? We need to do just what we did now before with the heights. Standardize. Standardize for Eleanor is 680 minus 500 divided by 100. So that's 1.8. For Gerald, it's 27 minus 18 divided by 6. So that's 9/6. .5. So Eleanor did better. She's 1.8 standard deviations above the mean for people who wrote the SAT. So I ask you the similar question. I asked you a similar question, but I want the answer in terms of percentiles. How did they do relative to their group in terms of percentile? So you already know the answer in terms of who did better, but I just want the percentile score because that often gets reported. When you get a test result from a standardized test, they don't tell you where you are in terms of standard deviations, they tell you in terms of percentiles. So what I need to look up is 1.8 and 1.5. So I look up 1.8 for the area to the left. So 1.8 is this one here, and 1.5 is this one here. So those are the results from the table. Eleanor is in the 96.41 percentile, and Gerald is in 93.32. Of course, she's still higher, but I've converted them into percentile scores. Very good. All right, so now I want, so that's a, so this by name, this is a, I mean, these together make a X type 1 problem. I need to standardize first, and then I find the percentage, okay? So that's like an X type 1 problem if you do those together. Now I want to do a backward problem. So I give these names just so that you realize, the main thing of giving them names is that you realize there's 4 main problems that you're going to solve in this unit. You need to be able to standardize and unstandardize, and you need to know how to use the standard normal table forwards and backwards. So that's like 4 things you need to know. That's why I label these exercises. So what if you want to do the backward problem now? So this is an X type 2 problem. If you don't like the labeling of these problems, that's fine. This is just if it works for you, okay? So this is a type 2 problem, a backward problem. So what we want to do is the backward problem. I don't have a lot of space here, eh? So let's, step 1 is to draw it. We do things backwards. I know it's a backward problem because I give you the probability and I ask for the units. So I'm going to draw it. And I have to find the position at 99%. So this, I want to know, so he's going to be in the top 99%. I mean, I can put that arrow higher if that helps understand what I'm doing here. So this is 0.9900, and I want to know how many standard deviations above that is. So I go back to the chart. Got to clean it up a little bit again. And looking for 0.9900, remembering that we've done this many times. If I left it marked up, you could see how many times I use this. 0.9900 is here. That's the closest one, so it's 2.33 standard deviations above the mean. Let me do that again. So it's 2.33. So we're 2.33 standard deviations above the mean. Let's convert that now into the units of the problem. So x equals z standard deviations from the mean, or 2.33 standard deviations. You have to go back to the top to get those from here. Let me erase this. To get those from, oops, from here, let me take those down. So we want, let's take the whole thing down. Put it here. All right, so I want this for Gerald, so I got to go here. 6 is the standard deviation, plus 18. So the score is $31.98. Very good. And I don't have I mean, it's just the score. I don't have any units, so I just leave it like that, 31.98. And the very last problem, I guess on this page, because there's still more problems, but on this page, what about Eleanor being in the top 5%? So to be in the top 5%, she's over here, right? She's up on top of everyone below her. To be in the top 5%, like here, Gerald, the way they asked the question, is in the top 1%, right? 99% below him. But I want to be in the top 5%, so where would that be? To be in the top 5%, so the trick here is to remember that every mark that I put can be perceived as above all those below it, or below all those above it. Okay, it can have two perspectives. So the top 5% would be where there's 95% below. So I can write that as 0.9500. And that's how I proceed. Very good, Nivette. So let's look up 9500. 9500 on the positive table. So 9500, 9500, and I go like this. Did I miss it? Yes. Okay, look at this. So 9500 is perfectly in between these. So what value do I use? You back at 1.72, which one? Yeah, that's not 9500. right. If we use this like we learned before, it's perfectly in the middle of these, so it's 1.645. 1.645. Oh, I can't put it there because I need to write there. So let me clean this. Hold on. So I get this from an average and so you get 1.645. And now that's step 1. Step 2. The z is 1.645. The standard deviation for Eleanor is 100. And the mean is 500. I really appreciate you guys putting out your answers. Even if it's not correct, it's fine because it guides the conversation and I know where you need input from me in addition to what I want to say. It's 1664.5. Any questions? So if you still are not sure, there's tons of problems you can practice. So go ahead and practice them. What I'm going to do is, unless you have precise problems for me, I am going to leave you to practice all the problems I've given you. And I'm going to move to regression now because I have about an hour and I think I might have to go back and review the scatter plots because well, I can ask you how many of you watched the scatter plots video, but given the limited time, maybe you didn't watch those, so let's see. So first thing first, do you guys have any questions about this? Very good. Very good, no questions. Okay, so you have several problems to practice. And I guess there's 2 more here that I didn't give you the answers for. I have the answers for everything except maybe these. Maybe we can just do these 2. And then you just have this quiz is online. You have the answers to this online. You have all the answers here to the practice assignment. You have these problems all solved. So you have solutions for everything except for these 2. Let's see if we can do these 2 together. Here before okay. Let's do these 2 together and then I'll go to those correlations. The relative frequency of observations for a normal distribution with a mean of 65 and a standard deviation of 10 that fall within two standard deviations of the mean is approximately. So in this one, which one would you pick? Do you need to make calculations or can you just pick one? Right, so it's just D. So you don't have to do anything. That's it. Okay, so you know every normal distribution has that same pattern, and there's no numbers that are competing with 95%. You don't have to be more precise than 2 decimals. And I already showed you on the standard normal table, it will round to 2 decimal places as 95%. So that's all you have to do. You don't have to do anything else. Try the next one. Unless you have questions. Oh, that didn't work. Okay. So a mill makes castings, a mill makes casting containing a hole which is specified to have diameter 6 centimeters. Due to variability in the manufacturing process, the actual diameter is a normal variable with a mean of 6 and a standard deviation of 0.25. The proportion of these castings that have hole diameter within 1/2 centimeter of specification, 6 centimeters, is, how do you answer that? So the diameter is normal with a mean of 6 and a standard deviation of 0.25. where x is the diameter. Right. So this is saying find the proportion of x in between .5 let's do this like this. So within 0.5 would be 5.5 to 6.5. If you were to standardize this, are you guys agreeing with me with what I just wrote? Do you agree? So if you standardize this, you see that you get 2 and 2 again. Now this is to 4 decimal places. So the question ends up being, and that answer is C. So you guys are good. You guys are on track. So it's a matter of interpreting what this said. The proportion of these castings that have hole diameter within 1/2 centimeter of specification 6. So that's within 1/2 of 6. Within is the plus or minus for people who are not aware. Okay, and then I just made some comments about using software. You can do commands like skTest, swilk, and qnorm in Stata, if you have Stata, or some other software. Excel must have something to check normality. Once you have a distribution, you can determine if it's normal or not. These are all tests of significance. We're going to talk about p-values and these sorts of things later, but basically these are tests to check if your distribution is normal. So software does that, including Excel. All right, so I leave the rest for you guys to practice. As I said, you have solutions to these on Moodle, and then all the rest have solutions supplied. So practice, practice, practice. So now I'm going to ask you if slow. I want to ask you for the GDS unit that I left you with, not this one. I'll just go get another copy. So the GDS unit that I left you with towards the end, I discussed two variable analysis. Now, how many of you watch the videos on scatter plots? Anyone? No one? So you watched it. So this would be video. I'm going to get the number for you. 17, 18, 19. In the StatsLongobardi list. So only two of you saw them? All right. So, three of you saw it? So see, this is the thing. I have half of you that saw it. And half of you that didn't. Okay, this is really important that we understand how to look at two variables at a time. You need to know, so I recommend everybody watch those videos, and I'm going to say a few things here. When we look at two variables, we're trying to see a relationship between them. Now, we're not saying that any kind of trend means one caused the other. We need an experiment to prove cause. However, there are some methods that have been developed in econometrics, that comes from statistics, that allows us to infer that there's a causal relationship. But without that kind of, sophisticated use of statistics, we really cannot impose an assumption that just because variables are correlated, one causes the other. So that's what we're looking for. We're going to look for correlation or trend between variables. And we tend to, if we are trying to attribute a relationship, we're going to differentiate between the response variable and the explanatory variable. And then, leave it. These could be with experimental results, or they could be observational, and they could be hinting at the need for an experiment. So we put the explanatory variable on the x-axis, x and x, right? And we refer to that as the independent variable, and that's the variable that explains or influences change in the response variable. The response variable, or have no time to review material, can't even come to class, that causes them to do poorly. So missing a class is like a proxy. It's something that we can measure, and it indicates to us that the student's going to do poorly. So they are related, but missing class doesn't necessarily cause that response. It's just a predictor, and there's some other variables behind that you would call a lurking variable until you identify what is the cause of the student doing poorly. Could it be a variable such as studiousness, how much a student studies? That's not going to be easy to measure, identify, or capture, and so for that reason we call it a lurking variable. So that's what I was saying about here. And then I also introduced an example about the relationship between number of bowls of cornflakes consumed and height, because I guess even still there are commercials with basketball players eating cornflakes or eating some sort of cereal, and implying that eating that cereal make you healthy and you'll grow tall. And if anything, the association, the marketing of a basketball player and the association to cornflakes is good for the brand. But if anything makes children tall in that scenario, it might be the fact that they can afford the cornflakes, they can afford the milk to put inside, and maybe that milk is what really helping them realize their genetic height potential. But otherwise, there are limits to height due to genetics, and cornflakes can only do so much. Well, not cornflakes, the milk that you eat the cornflakes with. So I just use as an example some data. I just made it up. It's not actual data. On children age 10, the number of cups of milk that they drink or consume a week, and their height. And there looks to be a relationship between the two. The more milk consumed, the taller they seem to be, even though this one's kind of an oddball. Okay, so we want to look at this data, and I explain how to draw. Well, we go through the process of depicting it and then answering some questions about the data. And the questions I want to answer are, first of all, I want to depict this as height versus cups of milk. That's the title of my graph. And when we write things with this versus, we always write y versus x. So this is on the y-axis. And this is on the x. Okay. And what we're implying here even though we haven't proved it with an experiment, it's just observational, but we're implying by putting X as cups of milk and height as the Y, we're implying that drinking milk leads to a taller height. But to prove that would require an experiment with randomized controlled experiment, or random comparative experiment. So if I plot these, the plot ends up looking rather tight. It ends up going something like this. And I even put a break in the chart so I don't have to start exactly at 0, and we can focus in on the area or the range of values. And then I go in more details in the video if you watch them. I have to comment now, is this relationship linear? Is there a linear trend here? And what I mean by that is, can a line approximate these values? Sorry, it's not a great line, but you can see so can we use a line in place of those points or those pairs of observation? Can we use a line in place and in a way that we can predict values that aren't there? So for this value of X, I could predict Y. That's the goal. So it does look like there's a slight linear relationship. Well, not slight, sorry, it's a strong linear relationship. So I'm going to make a point that this is yes and that it's strong, and then and it's positive. And I'm going to talk about the nature of positive and negative. Any questions about this? So what do you do once you have a scatter plot? You want to look at the overall pattern. You want to look for regularities and curiosities, any deviations from the broader pattern. Then you want to describe the overall pattern in its form. Is it linear or non-linear? And we'll talk about what we mean by that. And what is the strength and direction of the relationship? If it appears linear, then we can use the tools developed in statistics courses to calculate the correlation R and use it for estimation and prediction purposes. So I'll talk about what all this is. If you see a relationship that's curved or clustered, in these cases, simply state what you see. In higher level courses, you'd actually use a curve to make estimations and clusters to make estimations as well. But we're not going to do that here. So just to give you an example of what I mean about curved, you could have a relationship like this. This would be a curve relationship and you would refer to that as a relationship, but it's a relationship that's nonlinear. Okay, so it's a relationship, but it's a non-linear relationship. Another type of relationship you might see is something like this. Wrong color. And what you see here is if I'm to try and plot a line through the points, notice so I have to lay the line in such a way that it fits closest to all the points. Now it looks like it's a positive relationship, but it's very weak. Weak in the sense that all these points are far away, spread out and scattered. There's a gap here. It's not a strong relationship, it's very weak. Rather, it makes more sense to see a line that is that's not a good line. Let's try and move that. There. So it's better to see lines that are going in the negative direction. Okay, so that's very different than the positive upsloping weak line. These are strong and negative. So which one do we pick? The better fit are these two negative lines that separate the data. This is an example of a clustered relationship. And what explains it are two broader groups that behave similarly. There's a negative relationship between X and Y, but they're definitely set apart from each other. And what divides those needs to be determined. And then we can analyze and make predictions with each group separately. So I gave the example here as X being the number of hours watching soap operas or novelas, and I made Y the general sense of well-being. And it looks like the more hours of soap opera somebody watches, the lower their general sense of well-being. So as X increases, Y decreases. And I'm not saying that watching soap operas makes you depressed or unwell. It could be, however, that people that watch soap operas are either unemployed, or they're alone, or they're disabled. Things that make the day a little harder. And so it looks like the more soap operas they watch, the more immobile they are, or the more alone they are, the less content they are. Okay, so I just made up these numbers just as an example, and to show that it's not necessarily a causal relationship. Soap operas aren't necessarily making them depressed. That would need to be experimented on. But there might be another explanation. Now, what splits the data could be that women cluster higher because they tend to watch more soap operas than men. So I would have to look more into that data to see if that's the case. All right, so then that brings us to the second broader question. The second question is, can we predict what height of children will be if we know how much milk they drink? So would it be useful to calculate and interpret R, the correlation coefficient, to make predictions? So you should base your calculation on R on whether you have a linear relationship. R is reserved as a measure of the direction and strength of the linear relationship between two quantitative variables. Although this is just a sentence and it's quite short, it's it's very precise. The variables must be quantitative variables, and R gives you a measure of direction and strength of that linear relationship. So you need two quantitative variables and you need a linear relationship to calculate and interpret R. All right? Otherwise, it's meaningless what you're doing. So I provide some examples here. So I begin with R is an index. R is a value between -1 and +1. The more linear it is, the higher it is or closer it is to +1 or -1. The positive sign tells you the direction, or the sign tells you the direction. If it's positive, it has a positive trend. If it's negative, it has a negative trend. If it's 1, it's perfectly linear. If -1, it's perfectly linear, but it has a negative trend. So these are the extreme cases here. So here, R would equal +1, and here R would equal -1. Okay, now what if you have a relationship that looks like this? What would you say the R is? And what if you have a relationship that looks like this? What would you say the R is? So for the top, let's begin there. What would be the R here? I have to erase a few here. Right, positive but lower than 1. So let's say R is equal to positive 0.65. How about that? And what about here? What would R be? Yeah, it's like a negative 0.65. I tried to make it worse, a little bit worse, so I'll call it 5.5. When I have to put in another value, just to make it look more scattered than the above. Okay. All right, so let's look at the one on top for a moment and talk about what positive means. So what we're going to do is we're going to look at the range of values in this direction. Oh, let me put my X and Y on here. So this is X, and this is Y. So I want to look at the range of values for X, and we want to go about halfway through. So to be about halfway through would put us here. This would be X bar. Would you agree? And then we want to go about halfway through in the Y direction. To go about halfway through would put us about here, Y bar. And I'm going to erase this. And now I'm going to ask you, by doing this, what I've done is I've divided the data into values that are high, above the mean, and low, below the mean for X. And I've done the same for the Y, or the vertical direction. These are values above the mean for Y and below the mean for Y. And by doing this, now I have converted everything into a relative measure. Right? Statistics is about averages and relative measures. So now, when X is high, above its mean, where is Y? Is it high or low? So when X is high, Y is where? Is Y above or below its mean? Okay, X high, Y high, very good. So X high, Y high. Now let's look on the other side. When X is low, where is Y? When X is low, we're here, but where is Y? When X is low, Y is where? On the bottom or the top? Very good, it's below. So when x is low, y is also low. This is the nature of a positive relationship. X is reinforced by y. They go in the same direction. So it's positive because y follows x. Okay? That's what makes it positive. Okay? Now, if we do the same thing below, I'm going to split the data halfway through for x and halfway through for y. And I'm going to mark x and y. And now, when x is high, where is y? So when x is high, are we on the top or the bottom for y? Y is low. And when x is low, where's y? Y is in both places, but it tends to be high. So I'm going to say y is high, but the reason that it's not perfectly high, and there's some here, that affects this being perfectly negative, right? So it's this relationship that x behaves opposite to how y behaves that illustrates the negative relationship. This is a negative relationship. It's not perfect. It's not perfect. That's why it's not -1, but it's -0.55. And the last thing I want to say, what about a curved relationship? Let's divide, just like we did the other one, let's divide the x and the y. See, that's the middle of x, and then the middle of y is like here, right? So now what we have is when x is high, I have to add another data point to make this work. Okay. So now, when x is high, y is both high and low. So it's not clear. It's not a clear direction. And here, when x is low, y is both high and low. It's not a clear direction. When this happens, r turns out to be 0. Also, another example where you get an r of 0 is where you have no trend. This is called no linear relationship. Also, this is no relationship at all. There's nothing here. Okay, there's no trend at all. All right. What do I have next? I think that's it. I just have some exercises to practice. So practice those quiz questions. And if you need the answers, I think I have a video on the quiz, so you can watch the video. But those are the most important things you need before I go to the regression notes. Any questions about what I've just said? So what we're going to do now is get into the R. So you can watch that video again, like the edited one, 17, 18, 19, in the edited video playlist. And I want to start, I'm just going to talk about the regression formula and then, the correlation formula. And then we're going to go for the day. That's not what I wanted to do. So here is the formula for the correlation coefficient. What do you recognize here? Remembering that we only calculate this when we see a linear relationship between two quantitative variables. Otherwise, we don't compute this number. It doesn't tell us about nonlinear relationships. So for instance, when we had the curve, we had that curve relationship this is linear. This is nonlinear. It is a relationship, but you would get R of 0. The R of 0 tells you it's not a line, but there is a relationship, and only a graph could show you that. So it's really important to begin, just like any other data set, to graph the pairs of data to know what you're going to do next in terms of statistic calculations and summary statistic calculations. All right, so now looking at the formula, what do you recognize in the formula? Aha. And it uses the standard deviation and mean. And what do we call this when you do that? Do you see sigma? You see sigma? Oh, you see this sigma. Okay. So first of all, what do you call this when we do this? When we take x and we minus the mean and we divide by the standard deviation. What do we call that? All right, this is standardizing. So this is the standardized value of x times the standardized value of y. X and y are treated exactly the same. Because of that, it doesn't really matter for the calculation of r anyway. It doesn't matter which variable you have on which axis. It's not going to change the measure of r. It will determine what line you get, but in terms of calculating r, x and y are treated identical, so it doesn't matter. Then what happens? So after I do that, I multiply them together and I do this. What is this called? Remember, we call that the average. And I go through this when I talk about calculating the standard deviation, and you need to realize that whenever you see this symbol, you think of average. So I'm averaging the multiple of the standardized scores for x and y. So what happens is, if you have a relationship that is positive, when x is above its mean, what will this be on top? When x is above its mean, you will get a positive value. And when x is above its mean, for a positive relationship, y is also above its mean. So this will be positive. So you'll be multiplying a positive times a positive and adding a bunch of positives together. That will make r positive. Oh, this is regression, page 1, yeah, unit 3. Okay, so a positive relationship would put positive here and positive here. It would also, when x is below its mean, this term will become negative, remembering the standard deviations are always positive, right? Because the standard deviation is the square root of the variance. These are always positive. So when you have a positive relationship, when x is below its mean, y will also tend to be mostly below its mean. And what's a negative times a negative? A positive. So then you're still adding positives. So it's just a bunch of positives added together to make r. That's how it works. What about a negative relationship? So if you have a negative relationship, I go into the middle, when x is high, y is low. You see, when x is high, mostly y is here. So that means that when x is high, this will be positive, but y will be a negative because it'll be below its mean. And that will contribute, if you multiply a positive and negative, you get a negative. When x is below its mean, y is the opposite, it's above its mean. So when x is below, y is up here. So that will also contribute a negative. So you'll be adding a bunch of negatives together. And that's what will make r negative. All right? So that's a version of the formula that helps illustrate what creates r. It's 8:45. I'm going to let you go. I'm going to encourage you to look over the notes so that tomorrow will be a breeze. There are a few videos in regression least squares. I guess you want to work on the normal problems. That's your priority. If you have time before tomorrow's class, have a look through these notes. But I will finish regression tomorrow, and then that's Wednesday, and I guess start into probability, maybe not. Maybe we'll just solve some problems together. And then Thursday I'll get into probability. Okay? So do you have any questions? Okay. Valeria, you can just call my phone. I think we might have lost the chat because at some point my connection broke. So you might have lost the chat here. At any rate, you'll have the video. Okay, I'll say everybody, good night to everybody, and talk to Valeria, okay? Night for now, bye for now.